They are nature's very own Death Star beams, ultra-powerful jets of energy that shoot out from black holes like deadly rays from the Star Wars superweapon. These relativistic jets can be seen as bright flashes from Earth. But scientists have spent decades puzzling how these mysterious streams of plasma form. Experts have now moved a step closer to understanding them by measuring how quickly they switch on and start shining brightly once they are launched. The jets fire from black holes at the speed of sound when extreme gravitational forces squeeze matter until it erupts as a stream of plasma. Researchers found the stream accelerates across a distance of 19,000 miles before it gives off the typical visible light flashes used by astronomers to identify the jets. The study was undertaken by an international group of scientists led by experts at the University of Southampton. Dr. Poshak Gandhi, of the University of Southampton, told Mail Online, "In a nutshell, our findings tell us where above the black hole the jet is flashing in visible light. This turns out to be a distance of about 30,000 kilometers, very small in cosmic terms. This is also the size of the zone where the material is being strongly accelerated, so we can measure the distance over which the black hole is accelerating jet material to near light speeds. In Star Wars terms, the key measurement of this study can be likened to measuring the distance between the surface of the Death Star, where multiple rays of light shoot out, and the point where they converge into a single bright beam. But the physics of black hole jets has nothing to do with lasers or the fictional kyber crystals that power the Death Star. Nature has found other ways to power jets, said Dr. Gandhi. Gravity and magnetic fields play the key roles here, and this is the mechanism we are trying to unravel. Since their discovery, several theories have been put forward as to how relativistic jets are created. One theory suggests that they develop within the accretion disk, the matter sucked into the orbit of a growing black hole. Extreme gravity within the disk twists and stretches magnetic fields, squeezing hot, magnetized disk material called plasma until it erupts from the black hole. The jets fire in the form of oppositely directed magnetic pillars along the black hole's rotational axis. Plasma travels along these focused jets and gains tremendous speed, shooting across vast stretches of space. At some point, the plasma begins to shine brightly, but how and where this occurs in the jet has long been debated by scientists. The new research confirms that the plasma must come from the accretion disk, and puts an exact distance on when the jets begin to flash. In the new study, researchers used multi-wavelength observations of a distant binary system. The system is called V404 Cygni, and consists of a star and a black hole closely orbiting each other. The black hole feeds off matter from the star that falls through the disk, making it the perfect candidate to study how relativistic jets form. We used a fast camera attached to a large telescope to capture a movie of black hole systems swallowing matter, Dr. Gandhi told Mail Online. This black hole is located about 7,800 light-years away in the constellation of Cygnus. We also observed the black hole using an X-ray telescope in space at the same time. Our black hole movie captured about 30 frames every second. Our main finding is that this system first spits out X-rays, and then emits visible light flashes about just a fraction of a second later. This behavior occurred when the jet was strong. The researchers captured the data in June 2015, when V404 Cygni was observed radiating one of the brightest outbursts of light from a black hole ever seen. Using telescopes on Earth and in space observing at exactly the same time, they captured a 0.1 second delay between X-ray flares emitted from near the black hole, where the jet forms, and the appearance of visible light flashes. This marked the exact moment when accelerated jet plasma began to shine, allowing them to pinpoint the key event for the first time. The blink of an eye delay was calculated to represent a maximum distance of 19,000 miles. The study also creates a link between V404 Cygni and supermassive black holes, which lie at the center of massive galaxies. Similar jet physics may apply to all black holes, including these huge cosmic phenomena. The X-ray emission, representing the accretion disk feeding the jet at its base, was captured from Earth orbit by NASA's New Star telescope. The moment the jet became visible as optical light was caught by the Ultracam high-speed camera, mounted on the William Herschel telescope on La Palma, in the Canary Islands. At the same time, radio waves from the extended portions of the jet plasma were observed by University of Oxford astronomers using the AMILA radio telescope, in Cambridge, UK.